3D as shown here. You can see that this point A is not just shown as a vector line on the surface, but it's a 3D vector because you added F. You have used F to augment. You have used F to augment the vector, and so it is a virtual 3D space. Now, this has been explained to you before. Now, before I go on, this space here, in terms of coordinates, the camera position is always the origin of the image coordinate system. The camera position. And in this image, the camera is in the air. The image is formed at a distance f from the center of the lens of the camera. So the origin of the coordinate system for any camera is the lens position. And the lens position is always up, and the vector of any point from the lens position is given as bold letter A, okay, which of course embraces the X, Y, and Z coordinates. Now, the coordinate of the point O on this image will be a point where X is 0, Y is 0, and Z is going to be minus F. The coordinate of a point A here will be one that has X, XA, YA, and F. Okay, so the F is written as negative here because the image is supposed to be assumed to be a negative image. If we put it on the positive side, it becomes plus F. Okay, so the origin of this coordinate system is at the point, the lens position, and the as coordinate 0, 0, 0. The point below here will have 0, 0 minus F, and the point where A is will have XA, YA minus F. Okay, and you need to know that that's what this one is explained here on this page, where the coordinate of the lens of the camera has X0, Y0, Z0. The coordinate of the point directly below the camera, which is the principal point, has X is 0, Y 0, and F, Z equal F. For a point on the image that is measured, X, A, Y, A, F is the coordinate of the point. And we need to get used to that. Okay. Well, read what is left in that place. And I'll go straight to the last point for today. Will be to work an example, which I'm going to show you the procedure for doing that. Now, some lectures away, I explained the procedure for doing the field work, you know, for carrying out a close range image mapping. Okay, and of course that includes acquiring the data, right? And then the procedure for carrying out the calculations were also explained. But today we are going to see an example which you have to follow. Let me see how we can go. But before that, look at this page. This one, the title of this image, this section is the image as a virtual 3D space. Of course, we have discussed that. But look at this summary. The summary of the vector form of representing a point in image space is, in the Cartesian form, a point in the image will have A point A will have X, Y, and F coordinates. And in algebraic form, you can write it as X equal XI plus YG plus FK. That's what you have. In spherical, this is in Cartesian form now. In the spherical angle form, this same position vector is written as A, the magnitude of the vector, into cos V sine HI plus sine VJ plus cos v k. That's the same vector as the one you have up here. K is exactly the same vector. Now, in the direction cosine form, this same vector is expressed in terms of the angle that the vector makes with x-axis, y-axis, and with z-axis. So these are standard formulas which you can apply for a position in an image. Okay, where there are calculation procedure. This vector A in Cartesian form x, y, z in direction cosine form is given there. And R in this case can be computed as the magnitude of A, and that's what is given using Pythagorean theorem. Can compute the magnitude. Now you can compute the horizontal angle and vertical angle if you are given the direction angles. Okay, using this formula, H equal arctan x over z. These are converting x, y, z into the ROVH form. These are the formulas which we have demonstrated before. Just re-emphasize conversion process. Now, mathematical formulations for single image ray tracing. Now, the method we'll be using is called method of ray tracing. So when you are asked to compute the location of a point on the object using measurements on the image and then using the formula for ray tracing, what that is saying is that you have to use the formula for a ray, for a line that is a ray. And don't forget that a line that becomes a ray will be a line that has been separated into its direction and magnitude. And then the direction is specified plus the starting point. Then the line becomes ray. So, and that method is most commonly used in calculations of that we are going to encounter in this course. Now, let me go straight to, still have that line, have that. I've treated this before. Now, and these are many examples. I think this one we have also treated it. Okay, that's the end of that one. I'm going to share my next page so that after that example, then we can go home. Let me see this one. This one. Now you can still see my page. Let the class governor confirm that you can still see my page.
Yes, sir. I can see your page, sir. Yes, sir.
Now I'm on another.
Yes, sir.
Projection now, and I'll just go straight. All these ones you already have them. So I'll just go to I'm supposed to introduce this one to some of the lectures. I'm only interested in particular examples. Now, this, okay, that's already. Now, I have a simple example of how you can measure coordinates on a photograph. A photograph that does not have fiducial map that we can use to impose a coordinate system on it. So we are using this method to measure coordinate on the image. And what is done is when you load the image into AutoCAD, other graphic software like Idrisi, like MV, like ArcGIS image module, or any other image processing software, you can actually read off the pixel values. So each person will have to do a small field work, and that field work will require you to carry your camera, either the one in your phone or a professional camera, to take it to an area that you are comfortable with and look for a picture, a structure. I normally ask students to go to the student gallery. There is a student gallery opposite the chapel. That student gallery that has staircase from two up. You take the picture of that gallery and then use the measurement of coordinates or point on it to measure the distances between the steps from the minimum to the maximum. Okay, and then you can use tape to cross-check the accuracy of the calculation that you are going to make. But usually, after taking the picture in the field, download the picture into AutoCAD or any image processing software and read off the coordinates of the four corner points of the image. The four corner points of the image. Once you read off the four corner points of the image, you can do a rough calculation. The formulas have been provided as shown on my page. Okay. That formula that you have there, once you have read the pixel coordinates from the image, then all the x values of the four corner points are added together arithmetically and divided by 4. That means averaging the x readings and also averaging the y readings. These ones are the coordinates of the center of the image. If all goes well, the center of the image will be represented by those calculations. And then any measurement you now make later of any coordinate, by subtracting this x naught, y naught from them, the formula that you have on that page also give you the coordinate of any particular point that you have measured. But first of all, the x naught, y naught must be determined. This is like calibrating the image or calibrating the camera in order to get it ready for work. Okay, so you compute x naught, y naught as indicated there, and then any x that you measure will be calculated or reduced by the calibrated value. So any measurement by removing x naught, y naught from it gives you the xy coordinate of the point, which you can now use to generate the virtual 3D coordinate system for that image, x, a, y, a, and f. Okay, And when the procedure is explained there, I think you should ignore the next page, the next picture. Okay, ignore this one also, we have changed it. Okay, but the line that you have is the same as what we have seen before. Okay, now let's go to, don't forget that the line equation has been broken into P equal A plus ST, where S is the length of the line and T is the T bar, which indicates the direction. So this is the ray equation of the line. Now, when I ask you to distinguish between a ray equation and a line equation, the line equation is P equal A plus T into P minus A. Okay, but if I say the ray equation, then you say the ray is A plus S times T, where T is the direction of the line and S is the magnitude of the line. That's the difference between a ray and a line. Now, that is also repeated here in another form, where S is the length of the line, and then D is the direction vector for that, and then of course P naught is the starting point of that that ray equation. Now, this is another form of ray equation when you break it into X, Y, Z. But I will not bother you because we use this form when we are trying to find the intersection of two lines. Any two lines in space, if they converge, then at some point they must meet. And you are interested in knowing what that point is. You know, maybe you are trying to locate the corner of a building that we are constructing. And then you have one line coming one way, you have the other one. You want to know the coordinate of the point where they meet. So we use this one for that when we are doing engineering calculations. Now, yeah, that's the same thing that I've just explained, how you can derive that by deriving a simultaneous equation that you can solve for the values that will indicate where the lines are intersecting. We are not interested in that now. We're also not interested in alternative forms of equation. The line is a very important geometric object that is very useful in all calculation, field calculation, office engineering design, and so on. So there are so many formulas that have been derived by individuals, which would enable us to get different aspects of the line. Maybe asked to find a line that is perpendicular to another line. You know, you must be able to do that, locate where the corner point will be, and then another line that takes off at a particular angle. So you need many of the formulas, and they are all available, but you cannot treat all of them at once. Okay, now one point that is important is you may be able to, you may be required to transform a ray. To transform a ray means either multiply it to increase its length, or you want to rotate it or reflect it about a line, and so on. So what we do is to change either the direction, okay, or the starting point. When you change the starting point, you are shifting the ray. When you change the direction, you're changing the ray. Okay, so but unless you do the two, the ray will remain the same. So we have a translation, which is demonstrated here. When you get the material, you're able to see how it is done. Now, we have solved this one before, this problem. Which is given a line that connects two points, this and this. We have already done that. I think this is a more correct solution of that problem, which you have to look at. And then we have other problems that are given, and they are solved line by line. So this is supposed to be what we have. For those who prepared the PowerPoint for the previous one, we're giving you a good job. We have different work examples, okay, which you can look at your own spare time. But the last point that I was going to go to is another explanation of the of the virtual 3D. We cannot overflog it, but let's just move on. Okay, now this is the last page. This is the last page that we are going to treat today. Now, I need to remove this one that is blocking the line. Come down a little bit. Now, application sequence of the single ray tracing equation. You will recollect that we have done single ray tracing, we have done the equation, we have done the equation of a line. From that equation of the line, we have also derived the ray equation. Now, the ray equation is what we'll be applying for now. And realize the advantage of the ray equation. You only need the starting point and then specify any length along the line, then you have the coordinate. Because the direction will just give you the coordinate of any point along the line from here to infinity. Okay, so that's the advantage of it. So that when we determine the direction of the ray from the measurement we make on that image, then by just finding a distance, we can get the coordinate of the object point on the other end. So which is very simple. Now, the sequence is that to apply this ray tracing concept to single image processing, we proceed as follows. Number one, specify camera parameters, essentially the focal length, f, must be specified so that you can do a virtual 3D from the measurement that you are going to make. Then provide the camera position at the time of imaging, which is designated as P0, okay? And then the camera distance h from the object. When you want to picture an object, you have to position yourself in front of that object and then sight the camera to that object. Once you capture the image, then you can, if the focal length of the camera is known, and the initial point where the camera is held is also known, then of course, the distance of the object from the camera is also something required for single image work. For multiple image work, you don't need the distance of the object from the camera. Or if time permits you to do only single image measurement, then you need the approximate distance of where the camera is in relation to the object that you are mapping. Okay, because that will enable you to be able to do calculation. Okay. Now, we now identify and measure coordinates of points of interest on that image. And such a point is represented as P, XA, YA, PA, XA, YA. That means the point X and Y coordinates already measured. Then you now generate a virtual 3D vector for that particular point by adding the third dimension, which is the focal length. So the point now becomes a virtual 3D system where the measured coordinate X, A, Y, A is augmented by F, and it becomes a three-dimensional space. Now you compute the magnitude and direction of the image vector as, first of all, compute S. S means the length of the ray in the image, and that can be computed by the Pythagoras theorem, XA, YA, and F. You square them, or find the square root, then you get the scale or the length of the line. And of course, once you have gotten S, then the direction of the ray, which is indicated by dx, dy, dz, can be computed by dividing every coordinate by the computed scale or S. Okay, and that's what is indicated here. Okay. Then after doing this, the object space ray equation may be written as, assuming that R is identical, that means we are not rotating the line, which we shall discover to be what we call the normal case. When the imaging system is used in the normal case, then of course, there's no rotation, there's no tilt of the camera, and then the equation becomes simple. Now, the object space position now can be computed. P equal P naught plus S over F times HT. But it should be D. But it's okay. So now P naught here, that P naught is the camera position. The camera location, where the camera is at the time of the image formation. And then we have worked example. Oh, okay. Have a worked example. Now, this example, is require you to do some calculations. And I think the person that is able to present an answer to me in the next lecture is going to get a bonus mark. Okay. Now he's saying a single image was taken of a football field. Where a football field, maybe we'll have changed this one to a vertical building. Okay. With a camera whose focal length is 100 mm. The image of a corner point on the field has image coordinates minus 45, 48, minus 45 mm and plus 48 mm. Given that the camera was located in an aircraft flying at 700 meters above the ground, okay, compute the ground coordinates of the corner point. Camera position at the time of imaging is 200,000 meters by 320,000 meters. And then the height is 700 meters. Okay, this is actually using, this person is making an assumption of an area photogrammetry, whereas we are doing terrestrial. But for an exercise, that's a good one. You can manage it. We have another one for the terrestrial, which is our major concern in this course. Now, the working procedure has been indicated there. So you just need to follow line by line, and then you follow. You can see the same sequence which is stated in the procedure which you have before. This same sequence is what is repeated here. And then line by line, you can get to the solution, which is solution is given on this page. And that is where I'm going to stop today. We're going to meet possibly 2 times next week. I want to make sure I can end this lecture by next week so that I can do revision for both SVY 504 and SVY 528. Now, does anybody have a question where we are?
Sir.
Any question?
Yes, sir.
Okay, go ahead.
Yeah, my question is, okay, I was reading something on high resolution remote sensing imagery.
Okay.
For CRP, for close range photogrammetry, is it necessary that
come again?
My question is when we are dealing with close range photogrammetry, is it necessary that all our results must always be in high resolution, or coarse resolution also works?
I don't know whether there's any whether there is any special meaning to high resolution apart from either using high quality camera or flying low. You change the resolution of your image only by flying at different distances. An image that is taken at close range will have very high resolution, and the higher resolution than one that is taken at longer distances. So, but unless the camera design is designed to, to a higher specification where the resolution can be very high, I don't know whether there's any special interest other than get most accurate result. You all know that when the resolution is very high, then the image becomes clearer, measurement you make become more accurate, and everything becomes more definite. So I don't think you should worry yourself about what resolution is used. Bottom line is that the camera is designed for a particular resolution, and then you can now use it. If you want to change resolution, you have to, the only option you have, you can't redesign the camera. The only option you have is to either fly or either use it in a closer range or use it at a certain convenient range when the resolution will meet what you require. I don't know if I'm addressing or hitting your point.
Yes, sir, you've addressed my question already, sir.
Yes. So whatever the resolution is, the resolution is a property of the camera and is made at the time of production of the camera. Want to make a camera of so many resolution, or if it's in the ground unit, we call it what name do they call it in the ground unit? The resolution. We call it GSD, or ground sampling distance, right? Ground sampling distance. So if you want it to be 3 cm or 5 cm, then it is designed that way, and then the distance at which you get that resolution, it depends on you. The manufacturers will tell you this thing has a 3 cm ground resolution, or it has a 0.5 mm image resolution. So once it is like that, you want to use this for something that is either worse or better, you have to vary the distance at which you capture your image. Okay? Is that clear?
Yes, sir, it's clear, sir. Thank you, sir.
Any other question along the line? Any other question? So, I can see that there are more people online now. I have 18 people in the class now. Any other questions?
No, sir.
The people who do not ask questions, are they mesmerized? Are they humiliated?
You are listening, sir.
You are listening.
So Aziz, Jordan, ask your question now. Ask your question concerning the lab or the assignment or the test that you're looking at, so Prof can be aware.
Okay, sir. We're saying exam is fast approaching, and we don't have any CA yet.
Let me hear you. Let me hear you, sir. They're not very audible.
I said we have no CA yet. Then the exams are fast approaching, sir. So we need CA. So we shouldn't just be exam. We should just go straight into exam. It might not be lab entirely, sir. Maybe assignment also, sir.
Well, for the lab, I'm going to make it formal. I'm sure by next week we are going to get a lab. The lab does not actually take you time to do if you set your mind to it. Because all you need to do is to go and take a picture of any convenient place that you like, and then now try to specify the characteristics of the image, number of pixels in the image, resolution of the image, and then you try to measure coordinates from the image. Okay, so that lab will be given given along the lecture note that you are going to receive by before the end of next week. So, and it will require you to just go out, take your picture, get to the lab, take a few minutes, you have done your analysis, and then you write your report. Okay. Now, for assignments and maybe quizzes and so on, I want to make sure that I can do the lecture of next week, and then give you a laboratory assignment, which will be mainly calculations, and then also like along the line of things that you can expect in the exam. Is that clear?
Okay, sir. Yes, sir.
Yes,
Thank
sir.
you very much, sir.
Thank you very much,
Okay.
sir.
Now, please remind those who have
Hello, sir.
who are doing 504. Those who have done 504, that there's going to be a revision class, by either next week or week after. Is that clear?
Hello, sir.
No, I mean those who are doing 504.
Yes, sir, it's clear, sir. I'll tell them, sir.
Please tell them that there's going to be a revision class and they need to attend.
Yes, sir.
Hello, sir.
They have done their own lab. They have done their own lab. Am I correct? Tosi, am I correct?
Yes, sir. 504
sir,
students
yes, sir,
have done their lab.
Okay.
They should get their result this week, sir.
Okay, but they have to be present at the class, which they will arrange with me, and then we can do some revision and review some questions and how to answer them. Is that clear?
Yes, sir.
Okay.
Yes, sir. It's clear, sir.
Say yes. There are no more questions. Then we can end the lecture at this point.
Sir, I have a question, sir.
Okay.
Sir, I just got the materials we have to use for 528, and they are very bulky. So I'm wondering which one in particular should we concentrate on, because there are a lot, sir.
But if you use your money to buy, it's because it is free. Because it is free. If you buy a big textbook with a lot of money, I'm sure you want to read every part of it. The most ideal thing is for you to read all those bulky things so that you will be an overkill in the exam. If I were you, I would read everything. But like I told you, I'm trying to remove many of the unnecessary attachments and inclusions so that you have something smarter. And until I'm able to do that, hopefully this weekend I will do that. By the next lecture, maybe on Tuesday, if we can arrange it, then you are going to get the final one, which will also contain your assignments and every other thing. So manage all the ones you have for now. There are areas which we have talked about in the past. You concentrate on those areas where we have worked in class, and then try to avoid those ones that I did not say anything about. Okay. So what we are going to do, I'm going to give you a final one on Tuesday, and I'm sure that it will not be as bulky as it is. Is that clear?
Yes, sir.
Yes, sir. Thank you very much, sir.
Thank you very much. Thank you very much, sir.
No problem. Okay. 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 And I'm still around. Uh,